All right, good morning, everybody. Welcome to another cold but sunny morning of Chem 1105 with your host, me, Dr. White. Now, before we start our lecture, there are a few things I want to discuss with you. One, first of all, my glasses were dirty. Now they're better. First of all, if you come to my office hour tonight or any night that I have office hours, and you see on the screen when you log into Zoom, someone on the internet, that's me because nobody's there and I'm just looking around doing stuff on the internet. So if you log in, it doesn't look like me on the screen, just say something, they'll get my attention and I'll stop screen share, it's called. All right, second thing, more importantly, if you missed yesterday, or even if you didn't miss yesterday, I have already posted yesterday's mole practice review. And a lot of you should go back and look at that and then do practice problems. Because if you can't do mole conversions, guess what? You're not going to be happy with your score on test number 3 and on the final. It will not help your grade. You need to know how to do mole conversions. If you're having problems, always feel free to come to my office hours or see me after Tuesday lab or Friday. On Monday and Wednesday, I got to get ready for my class at the other school. Now, for today, I looked at the schedule and guess what? We're way ahead. We're not supposed to start the next chapter till next Monday. Today is Wednesday. Let me check. Yep, I was right. I just checked on my computer. And so what I think I'm going to do today, more than I'll think, I know I'm going to do today because I control the screen. But what I'm going to be doing today is because some of you last week were focused on, how do you like my new hand signals? Never mind. But anyways, we're focused on test 2. I'm going to go back and we're going to do today some more practice with chapter 6 material. And I'm going to cover it again with practice. This will help you for test 3, which is coming up soon. And let's get started. One of the important things you learn about gases, and that's what you're talking about. You think about the fact that right now you're breathing, you're surrounded by gases, you forget about that. But anyways, when we talk about gases, there are many things you can measure, and one of the most important is the pressure. And the pressure, which I'll never ask, is force per unit area. And how do you measure that? With a barometer. And what the barometer measures, do you have one in your house? I have them. Is what we call atmospheric pressure. And you should know, subtle Wednesday. That 1 millimeter of mercury, Hg is mercury, equals 1 torr. And torr is named in honor of the Italian scientist Torricelli, I hope I'm pronouncing it correctly, who did a lot of work with inventing and perfecting barometers and pressure of gases. Now, at sea level, I'm going to do something else new. I've never done this before. Don't you love when I can be subtle? At sea level, and Chicago is essentially sea level, when there's no storms coming through, atmospheric pressure is defined as 760 millimeters of mercury. And since 1 torr equals 760 millimeters of mercury, we know 1 torr equals 1 millimeter of mercury. We know 760 millimeters of mercury equals 760 torr. Now, also it's defined, and this is a very important unit, which is why I wrote that, 760 millimeters of mercury equal 1 ATM, which is not automatic teller machine, it's atmospheres. And you should know this. And because of this, you also know this is equal to 760 torr. And I don't have it open, so I better do that now. If you look on your screen, this is important information for test number 3. Again, I'm cutting down on what you have to memorize. And if you notice right here, I have 760 torr equals 760 millimeters of mercury equals 1 atmosphere. In the past, I had students memorize that, but good news, this will be on important information, test number 3. But you will have to know how to use this. So let's practice. And I'll do one, then I'm going to share the fun. And here, what are we being asked to find? And I might say, how many atmospheres is 725 torrs of oxygen gas, or just like this? Well, we're trying to find atmospheres. What are we given? This number. And what do we do? Well, this is the only thing we have to start with, so I'm going to start with that. And what do I want my answer to be in units wise? Atmospheres, ATM. Now, if I had a magic ratio, a ratio that I can convert this torrs into atmospheres, what would be here? And you know what's coming up. You're right. It's time for your good buddy, your good friend, unit analysis. I love that. Hopefully you do too. If not, well, just grin and bear it. Whatever we're trying to get to unit-wise goes on top of that ratio. Whatever we're trying to get rid of goes underneath. And now, remember, as I mentioned yesterday, let the paper do your thinking. So if I were taking a test, first I'd write this in instead of keeping it in my head. And then I would say, where do I find a relationship between torr and atmospheres? Well, it's in important information, test number 3. And here's 760 torr equal 1 atmosphere. 760 torr equal 1 atmosphere. So I can go back and say I have 1 atmosphere and it equals 760 torr. And if you notice, torr divided by torr is gone because anything divided by itself equals number 1, meaning it's gone or canceled out. That's a better way of saying it. And let me remind you, this is a definition. 1 atmosphere equals 760 torr. Therefore, both of these numbers, 1 and 760, are exact numbers. And therefore, the only thing that plays a role in our calculation is this number. How many significant figures? I'll give you 2 seconds. I gave you more than 2. Hopefully, you all came up with 4 significant figures. Therefore, my answer should be 4 significant figures. On test 3, like test 1 and 2, under your name, it will say, please use proper significant figures for all calculated answers. I have my calculator. Oh, look at the number I get. There are more, but I'm not going to write them all. And I'm going to let you round this off to the correct number, and then I'll do it. Time's up. You should have 4 significant figures. All non-zero numbers are significant. All numbers and zeros past the decimal to the right of the decimal are significant. So unless they're lead zeros, and that is not the case here, 1, 2, 3, 4. Use the 7 to round off. That's 5 or higher. I'm going to drop this, increase the 1 in front by 1. So I have 9.54. Are you seeing this? Yes, you are. Okay, I heard somebody's microphone. I wonder if you had a question. 5 times 10 to the minus 1 atmospheres. And that's how you do it. So I'm going to share the fun. And let me remind you, it's your turn. You do that all on your own. Am I nice or am I nice? Don't answer that. And since none of you have your webcam on except me, I'm going to have to poll and see if you're done. If we were face to face, I'd look around, I could tell when people are done. I'd also say, look up and smile when you're done. And some people would. All right, I think everybody's done. Let's get to work. What are you being asked to find? Torr. What are you given? 7.3 atmospheres. This is the only number I have to start with, so I will. And what units do I want my answer to be in? Well, I figured that out. Torr. And now I'll use my good buddy, my good friend, unit analysis. whatever I'm trying to get to goes on top of this ratio. Whatever I'm trying to get rid of goes underneath. As I've started talking about yesterday, let the paper do your thinking. So write this down. Don't try and keep it in your head. And where do I get these numbers? Well, someone was nice enough to write up here this. And we know 1 atmosphere is 760 torr. Don't forget, these are exact numbers. And this is how many significant figures? Oh, he's getting out of his rut. 2 significant figures. So our answer should be 2 significant figures. So now I'll pick up my calculator, clear it. That's an important thing to do when you're taking a test. And the calculator gives me this number. And if you put that down, I'll take off a point because I'll let you round this off to 3 significant figures. Not 3, I'm in my rut, 2 significant figures. Dr. White, look what's on the screen. Okay. All right, how do you round this off to 2 significant figures? You keep the 5, you keep the 5. Those are my 2. Use this number to round off. Is that 4 or less? Well, this is 4. So I'm going to drop this, and therefore the correct answer is this. And that's how you do that. Let's move on. Again,
Oh, I have a question.
I do questions.
Yeah. So the answers are I understand, but how do you get that times 10, 3, and then the first one was there was like -1. So I was just wondering how do you get like where do
All
you
right,
get these?
that's a very good question. Can you see my calculator all right?
Oh yeah.
If you look right over here, there's a
Okay.
tiny little 10. And there's an X there too. I don't have my bifocals on. But anyways, there's a tiny little X, then 10, then 0, 3. And on a calculator, that's 10 to the power. And if it was negative, let's see if I can do one, negative. All right, can you see that now?
Yes, sir.
You see where it's a negative 0.5
Yeah.
all the way over here? That's how you get it.
Okay.
Does that help?
Yeah, that helps.
And
Yeah, I
as
was using a different calculator. That's fine.
well, if you're having a problem with your calculator, either see me after lab, come to my office hour, or Friday, I'll have some time for you right after class. Sound good?
Okay, thank you. Yeah.
You're welcome. And as always, and I practice what I preach. Isn't that nice? There's no such thing as a dumb question in my class. And by the way, I don't know if I ever told you this. If I say I'll bet with you, I already know I've won because I hate to lose. I love to win even more. And therefore, I will bet with your question, there's at least 1 or more people in the class who had a similar question. So you not only helped out yourself, you helped out someone else. All right, let's continue on with chapter 6. Now, I talked about the gas laws. And gas laws, the term law in science, especially chemistry, I don't know about other disciplines, but I know for chemistry, means this is always true. No exceptions. If there are exceptions, it can't be a law. A law is always true. So the first law I'd like to talk about is Boyle's law. And again, we're dealing with gases. And why are we interested in gases? One, we breathe them. Two, back in the Industrial Revolution, to get power to power machines to make things. That was the Industrial Revolution of 1700s, especially in England. It started, or I don't know, started, but was quite heavy in there, or impressive. And the United States was coming on then, and so was the rest of Europe. I'm not sure about Asia, but anyways, when you're using a steam engine or now a gasoline or combustion engine, knowing how different measured properties of gases behave is very important. And Boyle's law is, don't worry about how it's spoken, is you should know P1 times V1 equals P2 times V2. Now, once again, I've cut down on memorization and an important information, test number 3, I give you Boyle's law. And I also remind you right here, P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, and V2 is the final volume. Now, everybody take a deep breath, let it out, take it in, relax. You're gonna do some algebra. Hope I didn't scare anybody, but I'll show you how. Two days later, I'll be finished. All right, thumbs up, people. Everybody see my whiteboard with the 8-point question? Thank you. All right, let's do this, and then you'll do one. And the first thing is, what are you being asked to find? And that is what happens to the volume of the balloon if the pressure is increased. So that's, you had initial volume, liters is volumes. So the new volume I'll call V2. And we're trying to find V2. What are we given? We're given an initial pressure, P1 equals 475 torr. You're given initial volume. Remember, liter is volume, torr is pressure. So the initial volume is 7.16 liters. And when the pressure is increased, that tells you the final pressure. P2 is 863 torr. Now, if we look at all this, I can draw an arrow better. hold on. It's Awful Arrow Wednesday. We look at all this, we're dealing with a gas, and we only have pressure and volume, which tells you you need to use Boyle's law, P1 times V1 equals P2 times V2. And in case you forgot, you can always go to important information, test number 3, and here's what P1 V1 is, here's what P2 V2 is, and here's Boyle's law. So what are we trying to solve for? V2. We want it alone on one side. Oh no, look, P2 is there. How do we get rid of it? Well, anything divided by itself becomes the number 1. Remember, anything divided by itself equals 1 is gone. Whatever you do to one side, you must do to the other side. And now P2 over P2 is 1. And I forgot to write here V2. Now I corrected that. And therefore, 1 times V2 is V2. And this side I have P1 times V1 over P2. Now, I like to rewrite this. You don't have to, but I will, because good habits I don't change. Never. Let's try to make it never. And now, since we took the time up here, we know P1 is 475 torr. V1 is 7.16 liters. And P2, if we look right here, we took the time to figure that out, is 863 torr. Now, before I pick up my calculator, I'm going to check what units cancel out, because I'm going to use a different version of your good buddy, your good friend, unit analysis. And notice I have torr on top divided by torr. They cancel out because anything divided by itself is the number 1. What units am I left with? Liters. Guess what? That's a unit of volume. If that didn't happen, you set it up wrong. We didn't. And now I'll pick up my calculator, clear it. Oops. And my calculator gives me this number. Times 10 to the 0. Remember, 10 to the 0 equals the number 1. And I'm going to let you figure out how many significant figures and what should be the correct answer. Because if you put that down, I'll take off 1 point for incorrect significant figures. All right. 3 significant figures, 3, 3. Oh, he's in his red again. So I keep the 3, keep the 9, keep the 4. That's my 3 significant. Use the 0 to round off. That's less than 4 or less. So I'll drop all that. So the correct answer is 3.94. And if you want to, you could write 10 to the 0, or you could just write 3.94. They're both the same. And that's liters. And that's how you do it. And guess what? I'm going to let you try one. All right, your turn. If a cylinder of argon gas, remember AR is argon, gas has a pressure of 833 torr at 1.05 times 10 to the squared liters, then what happens to the pressure if the volume is decreased to 1.01 liters? And I'll help you out. Remember, P1 and V1 are initial, and P2 and V2 are final. And P is pressure, V is volume. Your turn. I'm going to let you do this solo, and then I'll do it. And while you're doing that, I'll give you time to write everything down. No, I got it right. For a second, I thought I made a mistake. And two more rings, it will stop because it's not the Secretary General of the United States of the UN calling me. Oh, they gave up quick. And the votes are coming in. Give you a little more time. All right, I think we're done. All right, so the first question is, what are you trying to find? Well, it says what happens to the pressure. Well, that's the final pressure, P2. What are you given? The cylinder has a pressure, so that's P1. It has a volume. Remember, liter is volume. That's the initial volume, V1. And we're given if the volume is decreased. And that's the final volume, V2. And if you look at all this, you'll only see pressure and volume. Temperature hasn't changed. And we're dealing with a gas. So you use Boyle's law. And what are we being asked to solve for? P2. So we have P1 times V1 equals P2 times V2. We want to get P2 alone. Oh no, there's V2. How do we get rid of it? Anything divided by itself equals the number 1, meaning it's canceled out. So if I divide this side by V2, this will be gone. But whatever I do to one side, I have to do to the other. That's important. And now I'll rewrite this first. P2 equals P1 times V1 over V2. And because I like to, you don't have to, but I do, I'll rewrite it this way. And now, since I took the time up here to figure out P1 is 833 torr. And P2, V1, I'm sorry, is 1.05 times 10 squared liters. And it's important to put the units in when you're doing this. And finally, V2 up here, we took the time, is 1.01 liters. And now if I look at this equation or with the variables in there, I notice liters divided by liters cancel out because anything divided by itself is number 1. And what am I left with? Torr, which, yeah, it's a pressure unit or unit of pressure. And now, before I go ahead, remember on test 3, it will say, please use proper significant figures for all calculated answers. That's 3, 3, 3, always in his rut again. And my calculator gives me the following number. And if you put that down, I'll take off a point because that's not the proper significant figures. That's 2, 4, 6, 7. Actually, there's more in my calculator, but I got lazy. Why don't you round that off to 3 significant figures? Then I will. All right. And the answer is keep the first, second, third. Use the 9 to round off. That's 5 or higher. I'll drop this, increase this by 1. And that's 8.66 times 10 to the 4th torr. And that's your answer. And if you remember, if you have a cylinder and you reduce the volume, the pressure goes up. And that's how the compressor works at a gas station to fill your car tires. It compresses the air in a cylinder and fills up what's called a reservoir, or ballast tank is a better name for it. And that's how you fill your air. All right, let's move on. Now, Charles' law, we skip. I talked about it, but we skip. And if you notice, it won't be on a test or a final. It's even on your screen, written in print. So that must be true. And it is. I talked about the evaporation of liquids, and let's talk about that. I talked about the effect of temperature makes liquids evaporate faster the higher the temperature, and you form a vapor, and that vapor is the gaseous molecules that are gas, of a substance at a temperature and pressure where ordinarily would be as a liquid or even a solid. And there's something called equilibrium. That's when two opposing processes happen at the same rate. And there's also a term we call vapor pressure, and that's the pressure exerted from a vapor, the gas molecules coming from a liquid or solid above the liquid, in our case, when the liquid and vapor are in equilibrium. That means liquid is making vapor and vapor is condensing into liquid. And at that point, I talked about a volatile substance, which I won't ask on a test. We talked about boiling. And boiling is when the evaporation, a form of evaporation where the liquid state to vapor state occurs in the body of a liquid by bubbles. And the boiling point, time for Dr. White to be subtle. And this is not an important information. Test number 3, you're going to have to memorize this. And I'm never going to ask you what it is, the boiling point of a liquid, but you should know how to understand it. And that's the temperature which vapor pressure of a liquid becomes equal to the external, meaning atmospheric pressure exerted on the liquid. Warning, warning, Dr. White artwork, it's permitted to laugh your head off. If we had a beaker or pot of boiling water and we heat it, say, with a Bunsen burner or a hot plate or a gas stove, you'll start seeing bubbles. Now, bubbles have a lower density than liquid water, and therefore they rise to the surface and collapse. And they give off what's inside the bubble, which is water in the gas state, water vapor. And that's a gas. And the water vapor pressure, when that's equal to atmospheric pressure, that temperature is the boiling point of the liquid, in this case, water. Now, when you have this lower, meaning as you go higher on the planet Earth, higher altitude, the atmospheric pressure gets lower, which means you need less energy to heat the water to get the vapor pressure equal to now the new lower atmospheric pressure. And therefore, and this is something you should know, should know I can't spell either. At higher altitude, the boiling point of water decreases. If you go up to the top of the Himalayas, which Dr. White will never do because I'm not a mountain climber, never was, never will be. I don't like super heights. One of my less favorite experiences was having to drive back from a conference at a resort in Oregon, going back to, I forgot which city in Oregon I had to go to get my airplane to get back to Chicago. And I was driving down this road, and right off to the side here, there was a guardrail. And guess what? There was about a 500-foot straight drop because we were on real high altitude up in the mountains. And guess what? In front of me and behind me were these logging trucks with a lot of logs, and it was raining. And these guys are beeping at me because I'm going about 5 miles above the speed limit, and they wanted me to go faster. Well, I didn't, because I wanted to stay alive. But when you go high up in the altitude, the boiling point of water decreases because the atmospheric pressure is less. Oh no, I'm out of time. I'm finished. And with that, I'm going to say, first of all, don't forget tonight, if you need any help, come to my office hour from 5 to 6:15. And with that, gang gesund. Bye now.